Welcome back. This is our second video using the IQ trials data. Just as a quick reminder for you, we are investigating intelligence in the form of an IQ test. We have 4 different trials. You can think of this as year 1, trial 1, year 2, trial 2, year 3, year 4, and we measure IQ each time. We have GPA, which is one of our covariates, and SAT, which is another covariate. And we have 2 independent variables. One of them is teaching method, and the other one is learning environment. We've also done a blocking GPA. We've just taken GPA here and rounded it to the nearest value, actually rounded it based on those that are less than 1, less than 1 to 2, 2 to 3, and 3 or greater. So that we now have a blocking variable. Alright, so let's go ahead. Last time we used general linear model and did a bunch of univariate procedures. So just as a refresher, we did univariates for fixed factors, the one-way factor model. For analysis of variance, we did factorial model with our 2 independent variables. We did them as random effects, we did them as mixed effects, designs. We added in a covariate. All the things we've done throughout the semester, and now we're going to continue on with the repeated measures framework. So I'm going to go general linear model and click repeated measures. And just to get us started, we're going to name what our repeated measure is. Here is trials of IQ. I'm just going to call it IQ. And there are 4 levels. We've measured it over 4 years. I'm going to go ahead and click add and define. So this just sets us up so that we have our first in our dialog box, we have within subjects variables. We have the 4 different levels of our repeated measure variable that we requested. So we can put those 4 variables into our model. And we have the option to put in other things. We're not going to right now. This is between subject factors, and we have covariates. Our between subject factors, for just as a quick reminder, that would be things like our independent variables like method, teaching method, or learning environment. So if we run this now, we're ready to. We're going to pick a couple options first. But this is the equivalent of your one-way analysis of variance, but instead of being just one time point, we now have it over multiple times. So we call it one way, even though in some ways we talked about it being a mixed design. Let's go ahead and click Options. We're going to click Descriptives and FXIs. We can click Power 2. We're not going to do homogeneity test right now, just simply because we don't have a between group variable. And we'll do some estimated means. This is the equivalent of our post hoc tests, like what we did for our univariate models. And we'll be using our Bonferroni correction. Just a reminder, we're going to help us retain our alpha levels at a reasonable level. And click Continue. And we will see that there's no post hoc tests here right now because there's no between factor. If we put one in later, we might do some post hocs. We'll go ahead and plot this. We'll take IQ and use that on horizontal axis and go ahead and click Add. And we can include error bars. Let's see what it looks like. And click Continue. And that's all we're going to do. We'll go ahead and click OK. And now we should have our model for interpretation. Let's go up. Here we go. We have 4 different trials as expected. We have the mean of each one of these trials. Just starting off looking at these means, we see that we started with a 97, a 106, a 124, a 133. They're certainly increasing. And just from a practical, meaningful, informative way, if you know something about intelligence tests, these are pretty big jumps from 97 to 133. So here we see that we have a multivariate test. The multivariate test is, even though we're sort of using a univariate framework, we can also use our multivariate tests, which provide us with the difference between means in the ANOVA framework, the multivariate analysis of variance framework. One of the really useful things about this is that we'll see later on when we test for sphericity, if that should be violated, one of your solutions potentially is to use the multivariate test. And here we would tend to use Wilks lambda as our F value. So you see 4 different F values here. They just depend on whether whether they're liberal through conservative. It tends to be with Wilks lambda will be a little bit more conservative than univariate tests. So we see significant. This model is significant, and we see the eta value here for the multivariate test. So if we had to, we could use this, which would be fine. Let's go down. We also produce our sphericity, which is significant. That's like, you can think about this as if your Levine's test for analysis of variance, for variance, was significant. So in this case, we have a significant sphericity, and we review it and say that if that p-value is large, we have met the assumption, and it's not, so we have failed. And again, for those of you who've watched the first video, this data is generated for the differences amongst those independent variables, so it's really once we put in those other independent variables, we'll see this problem go away. But for now, if we had to, we know we could use the Wilks lambda test. As a side note for those listening, you tend to find when you have truly meaningful and significant data, many different tests like Wilks lambda and our other tests we'll see tend to make the same decision. And that's a good sign for us. So we can also see that when we go down to our tests of within subject effects, all of these tests here are significant for IQ. And one way to think about these are as a measure of liberal through conservative measures. The sphericity assumes sphericity. Obviously, we've failed that test, but we could go all the way down to the lower bound, which is a very conservative test here for our repeated measures design. And all of those tests, all of those tests we see are significant, which leads us all evidence to trails to that whether we use the multivariate test or a very conservative measure for our univariate test, is that there's a significant difference amongst times. And our eyeball test, when we first look at this data, tells us that's a pretty big and meaningful change over time. That is, if they're really the same person, starting with an average of about 100 and going up to a little over 133 IQ, that would be incredibly meaningful to you. So our next section here that we get is what types of trends there are. The linear trend is significant, and also there's a cubic trend that comes up significant here. So we'll probably take a look at that in the graphs. Even though we didn't ask for anything and we don't have it, it gives you a default between subjects effects. There's nothing really to look at right now there. Our estimated marginals with some standard errors come up. This can be useful to you to look at the means again, but this time with their confidence intervals. These are the estimated values we asked for. And then pairwise comparisons. We can see, looks like there's differences everywhere in our model amongst our levels. And let's come down, let's do our multivariate test again, and let's take a look. Here we go. This is a very useful plot. This plot we ask for confidence intervals around our values. We see that those confidence intervals are very tight around those values. And we see a trend going up here, and we certainly can see that the linear trend is occurring just as an eyeball test. So what's meaningful about confidence intervals is those confidence intervals help us say, it's not just a bullet point estimation. When I compare one confidence interval to another confidence interval, in many ways that's like doing an eyeball t-test for myself, or for you, as you're looking at it. So we can see there's not only are these meaningful, relatively large and meaningful differences here between almost a 10-point jump in IQ, and then here was obviously a 20-point jump, that their confidence intervals are non-overlapping. Well, that is your very fast and quick tour of a one-way repeated measures design, but let's go ahead and extend this out. Let's go ahead back to repeated measures, and we'll click Define, and we have the same model, but instead of just running the equivalent of the one-way model here, we're going to add in between subjects factors. And I can add in teaching method, and I'll go ahead and do both. I can add in teaching method and learning environment. If we wanted to, if I just put in teaching method, this would still be a split plot design, and we would have just one independent variable. It would be sort of, as we've talked about before in class, and if you're only tuning in here, that's fine. That's basically taking this trials 1, 2, 3, and 4, and then we'd be splitting it up by the two teaching methods. So like the first 300 people will get teaching method 1, and the second 300 people will get teaching method 2. And we can split it up even further with our second independent variable, which is learning environment. So now we have the equivalent of 100 person per group. They are in teaching method 1 or 2, and then they're in learning environment 1, 2, or 3. So we'll take a look at what that looks like. Let's go ahead and do some plots. And we'll remove this one. And on the, let's separate plots by methods and put separate lines by learn, and we'll put IQ on the horizontal axis. And if we need to, we can kind of come back and do another set of plots. So we're going to get a different plot for each of those methods. I'm going to keep those error bars going too. I find them useful. Estimated means, we can see that now we could look at all of these different estimated marginals at the end. And let me just remove this one. I'm not going to do that yet. You know, for some of these, especially some of the three-way interactions, it just might not be worth looking at up front. I might want to wait to see what's significant before I start digging through all of these post hoc comparisons that I might not really be permissible to look at anyway if the interactions were not significant. And our post hocs, I mentioned before, we could do traditional post hocs. We wouldn't use methods. There's only 2 methods. But if you wanted to, you could use learn and click 2 keys. I'm not going to do that for this example. I'm not going to show you the output for that for this example, but this is how you would do it, produce that. I'm going to go ahead and click OK. I'm just not showing you some of those things because it gets so much output that it doesn't make sense to talk about right now. So I'm going to go ahead and click OK. And we've just run a repeated measures design with 2 independent variables. We can see now under the descriptives, not only do we have IQ level 1, we have teaching method 1 and 2, and we have learning environment 1, 2, and 3. So when I've said before there's 6 groups with 100 persons, for time 1, IQ 1, that's trial 1, we have people in one of 2 teaching methods, and we have them in 1, 2, or 3 learning environments. So there are 1, 2, 3, 4, 5, 6 different groups. We can see their IQs. We can see 109 kind of stands out to us, and maybe some of this 89 stands out to us here. And we see IQ 2, IQ 3, IQ 4. Now we have the multivariate tests, and we see there is significance throughout. This is interesting because now we should be able to explain the repeated measure variable, our within variable, across method and learning. So we want to kind of, and one of the things that's really going to help us with that is that graph that we end up using. So what we end up doing here is, and we may need to use this just like last time. Last time we saw that these were significant and these do not assume sphericity, so that was good. And we go down if we need to use them, and we see sphericity is held up this time. And again, the reason is because the method of data generation was based at the level of three-way interaction. So the data were generated based on teaching method and learning environment, 6 different groups for each time period. But when I say data generated, I randomly generated this data with a simulation. But when you generate data in the real world by collecting data, your sphericity can be impacted by the way that you look at your data. If you are looking at it and you collapse across groups, that could give you some issues with your sphericity or your equivalent in a univariate test with your Levene's test for differences and variances. Anyway, we didn't violate it, so it just gives us permission to look at some of our sphericity assumes tests. And we see that both in the multivariate test, where IQ and all of the interactions were significant, we see in the univariate within measures that the IQ throughout all of the different interactions are significant. So in a way, it doesn't matter which we would report. I would say since sphericity was met, there's no reason not to use the sphericity assume, this first one, for each one of these to report that as your F value. If that were not met as it wasn't last time, we would either use the multivariate Wilks lambda tests, F test, or we would use maybe the most conservative lower bound. Again, all of these are significant. Everything is lining up. So regardless of which selection we were to make. When things are not lining up well, that's when we have more of an issue. We did some contrast here. We can see that there are some significant trends, especially when we get to that interaction, and that will be more meaningful to us. This interaction, the fact that the quadratic and cubic are significant could be important. We saw in the univariate tests where there were some interesting interaction effects going on. So we want to be able to explain the highest level interaction here, and this also points to well, we'll take a look at the graphs, but it also points to the fact that we may not have as much meaning in the, for the repeated measures as we, discuss in the univariate design. The main effect might kind of not go away, but the main effect isn't as meaningful as the interpretation of the interaction. And our between group effects, this is sort of like our old fixed factor model. We have method and we have learning, and that interaction, those are all significant as well. And here we go. So let's go ahead and interpret this. For method 1, we have IQ across the bottom here, kind of so we can see IQ over time. It's kind of neat. We see them all rising, but we see this major, well, we see a pretty big interaction going on here that in learning environment 2, that's kind of increasing and going above learning environment 1. So we also now see, let's go ahead and take a quick peek at method 2, and now we see something totally different kind of pattern. So in method 2, we see that the interaction effect has over time, that if you're in learning environment 3, it has the biggest impact. So let's go back a little bit, just the last graph to help us interpret this, because our job here, let me go back even a little further, is to interpret the interaction effect here. This main interaction effect is significant. We need to be able to explain that. We used it in our data. We have a three-way interaction, and we also see things like quadratic and cubic effects. Most people don't go beyond cubic effects. For explanation, they're not looking to explain something beyond that in our data. There'd be no reason to anyway, that we only have 4 time points. So in interpretation of our interaction here, we can see if you're in teaching method 1, that for each time period, IQ 1, 2, 3, and 4, that the learning environment, the third learning environment, which was that kind of, just as a recall to you, is that environment 1 was traditional face-to-face, environment 2 is a online only, and environment 3 is like this major interaction of face-to-face, online, and mentoring and other things. We see that is always consistently above for each time point, and it's increasing. It kind of has this bend here, so maybe more than just a linear trend. But we see that in method 1, there's some pretty good gains on the learning environment 2, and there's certainly not bad gains in our learning environment 1, the traditional method, but it's a very linear trim. We don't see that kind of bend in that elbow there. And then if we switch to method 2, we see that method 2 is not so good for learning environments 1 and 2. So let's go back up and see. This starts at 100 or less and goes up to 110 to 115 for those two methods. And we see we start at same about starting area, but for method 1, really big increase up to about 130. And for method 2, oh, you're going from somewhere around a 90 IQ all the way up to 140 plus. That's pretty big for method 1. And obviously for learning environment 3, it's good all around. That is, you would want to be in learning environment 3 here. Now for method 2, we see those start, the interaction effect here crosses over within method 2, and the learning environment 3 crosses way up top here. But these two learning environments, they don't do very well. I mean, they don't do bad. You wouldn't say a gain of 15 IQ points is poor, but relative for those in method 1 and 2 here, the types of gains that they have, 30 and 50 point gains in their IQ, you would want to be in teaching method 1 if you were in learning environment 1 or 2, and you would be, it wouldn't matter as much as you increased, you still would want to be in this learning environment here, but at least as you get into the later time points, these folks start to really kind of catch back up to their counterpoints in method 1. So it's a pretty complex discussion one would have to have, and hopefully one can start to see why we don't go much beyond three-way interactions. Once you start to do that, you have very difficulty. I mean, it can be difficult right now explaining this. The graphs are helping me out, but I certainly wouldn't want to do that explanation without these graphs, and I wouldn't want to have to do it with another variable. Like if I could add GPA as a blocking design, and I'm not going to do that right now for explanation purposes. What I am going to do is I'm going to go ahead and show you that the same model, if we wanted to, I can add GPA and SAT in as a covariate if I wanted to. I'm just not going to add this in as another between variable. So if I wanted to, I could use that exact same model and try to remove the effects of two covariates from this model. I'm going to go ahead and click OK, and we'll see if we have any differences, and we do. So when we remove the starting GPA and SATs, we can start to see that some of our models here, we can see that the interactions actually, it's just the interaction, IQ and SAT is not significant. Interaction with IQ and GPA is not significant. However, everything else did come up significant. Sphericity is still assumed, which is good. We want that to be over 0.05. And then our model here, well, actually all the effects are still significant. It's just the interaction effect of IQ over time with SAT and GPA was not significant. And in the end, we can see that we still have our two plots for our teaching method by learning environment by IQ. I'll show you the other one too. And what I recommend as you go through this, I'm going to stop this now since I've gone hit about the time for our video. But what I'd say is go back, stop it, pause, and try these on your own. All right. We may have a video 3 shortly as well.